Hello, now we are going to look at graphing sequences, and this again links in well to algebra and equations and functions in terms of our understanding of how we take a story, how we take a rule, and we're going to graph it. So let's start with our story. Jay makes a deal with their parents. For pocket money for doing chores, they get either option L is €6 on day one, so you get €6 up front and then you get €1 each day after that. Or option E, you get €2 today, but Jay's parents will double the total amount of money they have each day after that. So those are our two options. Now let's look at what questions we have to deal with. How much is Jay's total money for the first 4 days with each option? So let's start off then with part one. So let's start with option L. So for L, we start off with €6 on day one. So let's do our term numbers, or our days, on top. That would be our term numbers. Sorry, that would be N. And then we'll have our money, which would be our actual term numbers, underneath. So we can just keep track of what it is we're doing more easily. So we've got day one. Well, in option L, in day one, we just get €6. So our total money is €6. So again, we need to be careful about the language here. We're looking at the total, not the amount that Jay gets each day, but the total amount of money that they have. So on day one, they've got a total of €6. On day two, they get €1 more, so they have €7. On day three, they have €1 more, they have €8. And on day four, they have €1 more, they have a total of €9. So that is our situation for option L. Now, what does option E look like? And again, a table can be helpful. We can just do this out as a list as we have before. It's just that when we're comparing stuff, it's often helpful to have it written out in a table, and drawing tables is a skill we need to have. So we'll put in our days, and that's our term number. And then our actual terms, we know we call TN. So what's the total amount of money that Jay has under this option on each day? So on day one, Jay gets €2, so less than an option L. But on day two, that amount of money gets doubled. So that means that we would have 2 times 2 is €4. And on day three, we'd double the total that Jay had again, so we would end up with €8. And on day four, we would double this amount again, and we would end up with €16. So those are our two different situations, and we've drawn them as a table to try and keep track of them a little bit more neatly. But again, you can write these out just as lists to begin with. So you just have 6, 7, 8, 9, and 2, 4, 8, and 16. Now, that's our part one done. We can see how much money we get in total for each option. So that's part one done. Part two. TN for both options. So I've written this in brief because I wanted to try and keep everything fairly together. What this could be phrased as an exam type question is find an expression or find a formula for the total amount of money for any given day. So if I'm asked for how much money in total would Jay have with option L after 100 days or after 2 months, I want to create a formula that's going to tell me how much money they've got at that point. Or likewise for option E. So let's start off with option L. Well, option L, if I write out so let's write out L. That's 6, 7, 8, 9. Let's bring this up here. Well, what's happening going from one to the other? I'm just adding 1 each time. Well, that's my first test done. That means I've got a linear pattern. So I know I have a linear pattern. So that allows me to say, well, I know a formula for linear patterns. So I know that my two methods would be either my Tn would be equal to d1 times n plus some constant, or I know that I could have Tn is equal to my formula in my log tables, and either method should give me the same result, and I can do either of them out. So my difference here, for a linear pattern, it's the first difference. The difference of the terms is going to be constant. That's how I know I have these formulas here. It's not a quadratic pattern because it's not the second difference, the constant, it's the first difference. So I sub that in. I know Tn must be equal to 1 n plus k. And I also know that T1 must be equal to 1 times 1 plus k, and that must be equal to 6. So that means that k is 1 plus k is equal to 6. Rearrange. And k must be equal to 5. So that tells me that my formula must be Tn is equal to 1n plus 5. And I would get the same thing using my formula here. I know that a is my first term and d is 1. If I sub that in, I would get the same formula here. That should be a therefore or implies. So that's my first formula. And now I need to look at my option E. So what does it look like for option E? 2, 4, 8, 16. So when I'm doing this, I'm adding 2, I'm adding 4, and I'm adding 8. If I do that again, I'm adding 2 and I'm adding 4, and I run into a problem. I'm not adding on the same thing each time, even with the second difference. But can I see anything that does get me from one term to the other? Well, it might jump out that really all we're doing is multiplying by 2. So I'm multiplying by 2, and I'm multiplying by 2, and I'm multiplying by 2 each time. Now this type of pattern has a name. It's called an exponential pattern, where we're multiplying by something each time, same as exponential functions. So we aren't required to know a huge amount about how these patterns work, but if we write out this in another way, if we say that if we go back to our table here and we had our term numbers 1, 2, 3, 4, and we have 2, 4, 8, and 16. Well, there's another way that we could write 2, 4, 8, 16 if we think about it. That would be the same as 2 to the power of 1, and 4 is 2 to the power of 2, and 8 is 2 to the power of 3, and 16 is 2 to the power of 4. Now, can we see a connection between these two things? Perhaps we can. The rule for this pattern is if we see our value for n is here, and this is our value for Tn, this is Tn as well, can we see that the value for n is the power on the 2? So our pattern is just 2 to the power of n. So this is called an exponential pattern. So an exponential pattern. So how do we recognize our exponential pattern where we're multiplying by the same thing each time? In this case, we're multiplying by 2 each time. So we have 2 by 2 is 4, 4 by 2 is 8, 8 by 2 is 16. We're multiplying by 2 each time. What we do is write down our list as normal, and if we can spot that we're multiplying by something, then we can just write it down as we have here, and then we can say it's an exponential pattern. The other thing is that by process of elimination, we can look and see, well, is it a linear pattern? No, because it's not the same difference each time. Is it a quadratic pattern? No, because the second difference isn't the same each time. Therefore, we can say that it must be an exponential pattern. Now, in the long run, we will know about cubic patterns as well, where the third difference is the same. So the best of all is to be able to see, am I multiplying by something? And just have that as a test in the back of our minds. But at any rate, exponential patterns mean we're multiplying by the same thing every time. Now, part 3. We're asked to graph this situation, and that's the main focus of today. So we already have our tables drawn out here. So for L, if you think about how we would draw this, well, our days are going to go on the x-axis, and our money is going to go on the y, and we're going to do the same thing for our exponential for our E option as well. So if we look at where our graphs need to go, our n numbers, our x numbers need to go from 1 to 4, and our y numbers need to go from 0. We should always try to start at 0, but a minimum of 2 up to 16. So that's how we figure out how big our graph needs to be. So we draw that in, and we're going to do this in 2 different colors. We'll do L in our orange color, and we will do E in our blue color. So on day 1, we had €6 with our L pattern. So we go to day 1 and we go to €6. And on day 2, we had €7. So in the door 2, up the stairs 7. In the door 3, up the stairs 8. We know we're going up by 1 each time. We got €1 extra each day. And that makes sense now. We can see we got a straight line. We got a linear pattern. Now, what do we get for our option E, for our exponential pattern? Well, we start off on day 1, €2. So in the door 1, up the stairs 2. Next day, we go in the door 2, up the stairs 4. Next day, in the door 3, up the stairs 8. And next day, in the door 4, up the stairs 16. So we can see this pattern here with our exponential. I'll sketch it in. We can see how this exponential is rising very, very quickly. And this is one of the things that allows us to identify an exponential when we see it. It rises really, really fast. Now, quadratic patterns can too, but exponentials are usually even faster. And again, we're looking for, is it getting doubled or tripled or something like that each time? Now we can see our total money here. We start off on day 1 and we get a better deal. If we're J, we get a better deal just getting our €6 on day 1. But fairly quickly, option E becomes an awful lot nicer. We get a lot more money overall when we go with our E option, when we go with our exponential option. So let's link that in then to our part 4. Which deal is better for J's parents? Well, J's parents probably don't want to have to pay J too much money. So what this question means is which option is going to mean that they pay less money? Well, up to day 3, so up to day 3, it would make more sense for them to go with option E. So up to day 3, you would go with option E because our blue line is below our orange line here. And then after day 3, we should go with option L because after that point, the orange line is lower. We're paying less money overall to J. And that's what we would want as parents. We don't want to be giving all of our money away to J's pocket money. And that is what we need for graphing our sequences.